Oh, but it's just a tablet, and so it's a rectangle here, and the rectangle mimics the rectangle that is the screen. So if I'm in the upper right-hand corner of the rectangle, then I should be up there in the right-hand corner of the screen, right? So, yeah, I'm a technology addict. Okay. Say it again. Yeah, I know, right? Oh, wait, you work at BrandSmart? Oh, that's no problem. That's no problem. You know, as your advisor, discount. I'm just saying. Wait, is that on tape? See, now I'm already recording. Now it's bribes and everything. I'm going to be fired tomorrow. I will be editing that out. I usually don't edit out anything, so I probably could get in a lot of trouble for some of the things that I've said. Speaking of which, we should close the doors. Okay. This is usually the format in which I will be writing notes in Smart Notebook. I'll print this as a PDF and I'll send this to you as well. Okay. So after the class, what I found though is people still vociferously still take notes, which is fine. And actually I appreciate that because it has to be in your words, right? You have to make your notes your own thing. All right. Oh, here's the structure of the class. We're going to be covering Chapter 5 from the beginning. Chapter 5 is the integral. Chapter 6 is applications of the integral. Chapter 7 is integration techniques. Okay, and then Chapter 8, I believe, is power series and power series. Sequences in series, and then Chapter 9 is power series. Okay. Test 1 is going to be on chapters 5 and 6. Test 2 is all of chapter 7. And test 3 is chapters 8 and 9. And then the final is everything. Okay? I'll be saying that a lot as we go on. Most of the class is about the integral. Okay. I'll take questions about the pace of the class. Review. F of x equals the tangent of x. Please. F prime. Secant squared. All right, now let me say, who didn't know that? Who forgot that? Okay. Cosine. Okay. Okay.
I knew it was something squared x.
G of x is equal to e to the x. G prime of x is e to the x. Okay, very good. Reviewing h of x, the natural log of x.
1 over x.
1 over x, very good. Step it up a level here. Secant of x squared. What is the derivative of that? Secant of
Secant x squared cotangent.
secant tangent, but okay, so secant of what?
X squared.
Of x squared.
Tangent of x squared
Times the derivative of x squared. All right, seems like we gotta run through these. Let's do it. All right, so let u be a function. I haven't given a definition for the derivative, and it's been a while since I've taught part 2 of a class, okay? But stone cold, you're supposed to know what the derivative is. What is it? The derivative is slope of the line tangent to the curve, really good. What else? And the instantaneous rate of change, right? So if I only gave you 3 words for the derivative, rate of change. Sir?
That's not going to be question 1.
No, it is not. It's not.
Is there going to be a question 1 for every test?
I think so.
Yeah.
I think so. I think you're going to define the integral. I think we're going to do that. But we'll see. let u be a function of x, then here's what we spent all of Calc 1 doing, right? And justifying the derivative of u to the n of that function to the nth power is, what do? What's the derivative? It's n, you bring the n down, and then n minus 1 times the derivative of the function. And so it seems like we need an example. The derivative of x squared plus 3 to the 90th, the derivative of that is 90 times x squared plus 3 to the 89th times 2x. I'll take any questions on that. What rule am I using here? The chain rule, right? It's the power rule within the chain rule, that's right. Okay. The derivative of e to the u is e to the u times the derivative of u. The derivative of the sine of u is cosine of u times the derivative of u. The derivative of cosine u is what? Is negative sine of u times u prime. Please, roll through the rest of them. Now, I've said that the class is about intervals. I said the whole class is about intervals. Why in the world am I talking about derivatives? Right, so for some reason we'll need to talk about antiderivatives, right? Okay, so 4.8 in Calc 1 talked about antiderivatives, okay? So somehow antiderivatives and integrals are related. Now they're so related that we often just interchange the two. And to do that is to forget the history and the brilliance of the subject, okay? So we're going to distinguish between antiderivative and integral. They are not the same thing. Okay. So for those of you who are well versed in the story, bear with the rest of us. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. That sounds like someone who just had this over the summer. The derivative of, what am I missing? Cosecant. Derivative of cosecant. Negative cosecant of u, cotangent of u, times the derivative of u. And the derivative of secant is secant u, tangent u, times the derivative of u. The inverse sine. Well, let me go ahead and put the natural log here first. The natural log of u, the derivative of it, 1 over the function times the derivative of the function. Okay, now let me also say that if I want to make this a PDF, I cannot extend more than a couple of times so that it looks okay. So, inverse trig functions. The derivative of the inverse sine of a function do you remember? 1 over the square root of 1 u squared times u prime. Perfect. The inverse cosine? Right, it's the negative of this. I gave some extra credit about that last semester. And then last extension, the derivative of the arctangent. No. It's 1 over 1 plus u squared times u prime with no square root. Right, so there they all are. Okay? So, like the back of our hand, you know these. Right? Like the back of our hand. Right? So we're going to need to know these, and we're going to need to know these because, and by the way, you have to ask that of me. Why do we need to know it? Right? You need to ask that. Right? If I'm not telling you, you need to say, why are we learning this? Why are we learning this? Okay? We're learning this because there is a connection between, if we want to talk about integrals, we need to know something about derivatives. Specifically, we're going to need to know something about moving backwards on this list. So that when I give you cosine, you're going to have to know that the derivative of sine is cosine. You're going to need to know the antiderivative. Okay. Questions about that? All right. Who knows these cold? Okay. Make sure you know them cold, okay? We are going to start in chapter 5. All right, and so the question is now, we want to have a function, and we want to find the area under that function, okay? So here's some axes. Right? And draw a function. There's the function A, B. I also have the charge, the personal charge. My colleagues don't do this a lot. But I also want to make it relevant. Right? So I want to be talking about problems that matter to you. Okay? So, so as we go on, particularly in chapter 6, we'll see lots of applications of the integral and why it's important. Okay? Right now, we're just going to formulate it. And by the way, I think that that's a backwards way of doing things. Right? I think we should talk about the problems first, and then formulate the theory. But my mathematical brothers, myself included, right, we often talk about the concept first, and then we get to the problems. Of course, we know by that time I've lost many, many people. Right? So bear with us with the patience here. Okay, so I want to find the area under this curve. So from A to B. And so I want to find this. Right? How much is that? X, this is X, right? And this is Y. This is f of x. Okay. This is a difficult problem. So what do we do? What we do with difficult problems is we say, can we solve the easier problem first? Well, what's the easiest problem here? Well, an easier problem would be, can I find the area under this function here? Here's f of x right here. Just a straight line, okay? So f of x, let's pretend that's a straight line. It's equal to 10, right? On the interval 0 to 4, I want to find the area under that. No brainer, that's 40, right? So that, and here's a unifying concept I'll say over and over and over again. When it's constant, we know the answer, right? And so we're going to use that for this. This is not constant, right? This is changing, right? But we're going to use, but in certain places, it looks almost constant, okay? So what we're going to do is, we're going to use this principle to answer our question here, right? Who's seen this formulation before? Okay. Who knows what the integral is? Okay. So it's not that much of a review. What we're going to do is we're going to take the interval a to b, right? And we're going to break it into pieces. Does that sound familiar? Okay. Now I'm starting off slow. I'm only going to give you an approximation. I can't even think about giving you the exact answer to this, right? I just want to get an idea of what the answer could be, okay? Here's what I know. I know that this rectangle here, I'm going to claim that I know exactly the area of that rectangle. Why is it that I know the area of that rectangle? What do I need for a rectangle in order to know the area? The length and the width, right? Now, here's this rectangle. Here is the width. Here's the length, okay? Now, how do I know the length? How do I know the height? Because I know what? I know the function. The function will be given. So I know the height at any point. And why do I know this distance? Because I got to decide. Because I picked it. Okay. So I'm going to decide how many pieces I want to break this up into. Okay. So that I picked this distance, and now that I know this number, I can plug that number into the function and get the height. And therefore I know the area of that rectangle. Is that okay? Questions about that? Now, I can do this any way that I want, and I'm going to try to do it in the easiest way possible. I'm going to do it in a couple of ways, and I'm going to have to justify that it doesn't matter how you do this, okay? But here's what I'm going to do. I'm going to do this in such a way that each piece is of the same length. It only makes it easier for me, okay, to do it that way. So each piece is of the same length. If that's true, right, and I have n pieces, what is the length of each piece? What's the total length? What's the distance from here to here? That's a b. I'm sorry. It's b minus a. That's right. So the whole distance is b minus a. And I have how many pieces? N of them. That's the length of each one. We call that delta x. Is that okay? And then now I've been biased. I drew this rectangle, but what did I do here? I picked this as the height of my rectangle. I could have picked my height to be whatever I wanted. So that now in this subinterval, I picked this to be the height. But now in this subinterval, maybe I wanted to be an ass. And I want that to be the height. All right, so now I'm just going to go ahead and in each subinterval pick a height. All right? The width is already determined. I've made it the same on each subinterval. Let's pretend that they're the same, right? So now, whew. So work our way. Next time I'll just do a couple, okay? Okay, now I'm being biased. I need to stop. So now I'm going to go here. I'm going to do this one. I want that to be the height. Right? So in each subinterval, I have the choice of making the height whatever I want it to be. Now, of course, when we start doing these, we're going to be pretty uniform in what we pick to be the height. In each subinterval, we're going to pick the height to be the same thing. And ultimately, you're going to have to ask me, does it matter? And it's not going to matter. That's the only reason why I can just uniformly pick it to be one thing. Right? So notice here, for the height, I wanted it to be, it's the right endpoint. In this subinterval, it was the left endpoint where the height was taken. And this subinterval, it was the left endpoint. And on this point, I got into a pattern. I started picking the left endpoint constantly. In this subinterval, I picked the right endpoint, right? In this subinterval, I picked the right endpoint to be the height. Right? Is that okay? The point I want to make, of course, is that this area, including this, right? So this area here, these are rectangles, right? We can do rectangles in our sleep, right? We add up all those rectangles, and we know all of this stuff. Then that's approximately the area under the curve. Questions on that? All right. Question number 1 on the exam is define the integral from a to b of f of x dx. That's question number 1 on the exam. Define the integral from a to b of f of x dx. I have not defined it yet, but that is the first question. And the second question will be to approximate one of these areas. Okay.
What's question number 2?
Define the integral from a to b of f of x dx. Thank you for your question. I'll write it down too when the time comes. Let's be concrete here. Let's get a function here. Let's do x squared. I got so much stuff here. Where are you? There you are. So we'll do a supposedly simple function, and we want to know the area under x squared. And let's say on the interval 0 to 1. All right, so is it going to do it for me? No, it's not. So because I have to label, I have to give the domain. All right, so there it is. I'm going to know the area under the curve. Someone tell me what it is. Someone knows what it is? Well, okay. It's not easy, right? We'll approximate it. So it starts off at 0, 0, ends up at 1, 1, right? Prove to me that the area is less than 1. Prove to me that the area is less than 1. That's exactly right. The whole box is 1 by 1, right? The whole box is one unit by 1 unit, and therefore the area of the whole box is 1, and clearly the area in the graph is less than that. Okay, so that's a pretty easy proof. Okay, but what is it? It's 1/3. It's 1 over 3. Did you know that? Yeah. Okay. So that's exactly the answer. We'll approximate it first, see if we can get an idea. So let me go ahead and I'm going to take this. Okay, so. Too big for me. Well, maybe not. Maybe it's big enough. We'll sign that. No, we'll keep it big. That's fine. Okay, so now I want to just, it seems like it's done it for us. Let's go ahead and take these as rectangles, okay? So I'm going to take 0 to 1, and I want 5 rectangles, okay? So I'm going to approximate the area using 5 rectangles. Now again, I want to reiterate the power we have. I've chosen the number 5, and now that I've chosen the number 5, right, that automatically gives us the what of the rectangle? The which one? The width. That gives us the width of the rectangle already. Why? Because the width is 1 minus 0 over 5, and that looks like 1 over 5, which looks like the 0.2 they decided to do it. Right? So that's already pretty nice. Okay. And that's 0.2. Right, so Maple has decided to put it in terms of intervals of 0.2, which is great. So we have the width. What else do we need? We need the height. Okay, so now that's again up to us if we want to approximate. And now, and so that means in this subinterval, the first subinterval is of length 0.2, that's this. The second one is this one, and so forth, okay? Now, we get to pick the height, and I'm now going to say that I want you to pick the height by going in each subinterval and picking the rightmost number to be where the height is. And so we call that the right endpoint method. Now again, we have the choice. We could go in and pick whatever point we want to get an approximation. but we are going to use the right endpoint method. Question number 2 on the exam is going to say this. Here's f of x. F of x is x cubed. Okay. I want you to approximate the area under x cubed on the interval 0 to 10 with 5 rectangles using the right endpoint method. All right, that's question number 2 on the exam. All right, so it's almost like this. Okay. So we're talking about this rectangle, and then this rectangle, and then this rectangle, and this rectangle. Now, Mabel already has a program that does this. I'm going to be using it in a second, but I think it's important. I'm tripping. Wow. They go all the way up? How? They go all the way up to 1 or not? So weird. Okay. Oh, I didn't copy and paste all of it. Okay. I was about to say this. Okay. I just didn't copy and paste all of it. Okay. Is the answer more or less than the real answer? It's more, right? So the answer is already too much. I claimed that the answer was exactly 1/3. As a matter of fact, I'm going to put that on you. He said the answer was 1/3, right? And he happens to be right. Okay. Let's figure out what our approximation is. So we just simply need the area of this rectangle. Well, it's just the base times the height. The base is 0.2, right, times the height. Well, what's the height? This is f of x equals x squared. And I want to know what the height is at 0.2, so it's 0.2 squared. That's the area of the first rectangle, plus, and maybe I'll just draw arrows now, 0.2 times what? 0.4 squared for sure, and I hope we start seeing a pattern, plus 0.2 times 0.6 squared, plus 0.2 times 0.8 squared, plus 0.2 times 1 squared. All right, and we'll go ahead and put the arrow. So this one goes to this, right? This area goes here. The area of this one goes here. The area of this one is this. And the area of this one is this. Any questions? And that's the answer. And you can leave it like that on the test. Okay. When I see that you've done that, I know that you know the right endpoint method. I'm convinced, right? I don't need you to give me some decimal that'll calculate that. I don't need to see that, right? Because everyone can do that, right? Questions about what I'm asking? If I say the left endpoint method, is that okay? We would be able to do that. Okay. I'm probably going to ask the left endpoint method. Okay. I'll give some homework on this too, okay, in my math lab. Please, sir.
The left endpoint method would just start at 0.2 rather than 0.
Oh, what would tell me with the left endpoint? You're going to make me do it. Now, the left endpoint
I'm
method.
just saying that's safe to do.
But what would it be? 0.2 times what? 0 squared, right? Because 0 is the leftmost endpoint here. 0 squared plus 0.2 times 0.2 squared. And so now this one is left out.
Okay.
Yeah. You just shift everything to the left. What do you think the midpoint method is? You use the midpoint. And so indeed it's 0.2 times, what's halfway in between? 0.1 squared plus 0.2 times 0.3 squared plus 0.2 times 0.5 squared, right? Argue to me that that one's better than both the left and the right endpoint.
Takes the average somewhat.
It takes the average, that's right. So the right endpoint's too much, right? The left endpoint's going to be too little, and so the midpoint's in between. But we know the answer's in between. So if the answer's in between and the midpoint's in between, then that's obviously closer. Please.
So if you did the right endpoint method and the left endpoint method, what average is that? Would you get the same answer as the midpoint?
That's a great question. The answer is no. Okay, the answer is no. Not necessarily. Because you're taking averages at different places, right? So so you have to ask, you're adding two numbers and dividing by 2, right? Now, if we add the two numbers to divide by 2 and then square it, that's different from doing this whole process, adding those two numbers and dividing by 2. Those are two different things. So you can't get the same answer. Okay. Questions about that? Questions about what I'm asking on the exam? Okay. I'll be writing it soon. Okay. So what is that number? Does anyone know what that number is? We'll calculate it. Let's go into Maple. Maple does this for us for pretty straightforward. Doing some calc. We're doing. What are we doing? Approximate integration? I think I clicked on the wrong thing. Let's see here. I did click on the wrong thing. Close this. Tools, tutors, single variable, that. All right, so there's one for sine. We have x squared on the interval 0 to 1. And how many rectangles do we have? 5. And we're using the right endpoint method. Let's see what the number is. Let's display it. There it is, 0.44. Right. My man said the answer was 0.333333333. Okay, he's right. Okay, so but too much. All right, and if we do the left endpoint method, display, right, too little, 0.24. Okay, so too little. Okay. So again, left endpoint method, the first rectangle, nothing. So it's 0.2 times 0 squared, no rectangle at all. That's why there's nothing there. And then you just add them up that way. Right. Midpoint method, take the midpoint, 0.33. Let's write the 2 decimal places. Right. So that's pretty close. Okay. There are a group of mathematicians called numerical analysts who do nothing but this. Right. Try and calculate these types of intervals, okay, or these areas, I should say. Then we got random. Again, nothing stops us from just going in and just picking some. Here, none of these, they didn't pick the right, or this looks like a right. It looks like in this last interval they used the right endpoint method. But then here, who knows why they picked this to be the height, right? Random. Here, why did they pick this one? Right? So just random numbers to be where the height is, right? Here's the point. The point is that we want the exact answer. We want the exact answer. We want 1/3. That's the real answer. How are we going to do that? What are we going to do to that? We're going to take a lot of them. So randomly, it's random now. It doesn't matter what the height is. I just need to take more of them. That's why it doesn't matter, right? So you take a random height wherever you want it to be. Doesn't matter the order. You get a little bit closer. All right, let's raise the level. 160. Random height, right? So the more rectangles you take, the closer you get to that real answer. Any questions on that? Our intention, of course, is to go through this process, pick a number of rectangles in, and then let n go to infinity. And that will be the definition of the integral. Okay? Questions about this?
How is it useful to find the area under the curve?
We'll spend all of Chapter 6 talking about that. And again, that's a great question. Everyone should ask it, right? But it is the case that there are going to be some graphs, right? So you're going to have a graph that you may have a graph for you that represents something involving money, right? And you're going to want to know the total amount, right? So if it could be something like this, right? So this graph could represent something important to you, and literally, it should not be so far-fetched. And we'll come up with a bunch of examples in Chapter 6, but it should not be so far-fetched that we might want to know, well, what is the totality of all of this, right? It might be accumulations, it might be earnings or something like this. What's the total amount of money that you gained, right, If f of x in this case represents the amount of money that you earn per year, and you want to know the total, then you need to find the area under the curve. Right? That's what we're talking about. For those people who've taken stats, who's had intro to stats here? Very good. So what are we talking about? We're talking about, for you, did you raise your hand as well?
Yeah.
Okay. So we're talking about, for you, just this curve, and we all know it, right? The bell curve, right? So this thing, right? Whew. Can't get away with that one. This one.
There's a lot of anomalies.
Say it again?
So there's just a lot of anomalies, that's all.
That's right. Right. So this is 0, right? What is this graph? Say it again?
The bell curve.
It is a bell curve. What is it? We're in Calc 2. F of x equals 1 over the square root of 2 pi e to the minus x squared over 2.
Yeah.
That's what it is. That's what you were going to say? You're going to say that? That's what it is. Right. But I do want to mention to you how brilliant you are, right? Because you're in Calc 2. That's the function, and that's what people look up on the table when they turn to the back, table A in the back of the book, and they say, well, you know, what is the value of this and this? They're just talking about the area under this curve. So that when they say, well, how many people are within 1 standard deviation of 0, then literally they're talking about, you look in the back of the book, and they're talking about that area. Right? So in stats, all they're talking about is the area under the curve of that particular function. Okay. So that's one of the big reasons why areas are important. So what must be the case? It has to be the case that the area from minus infinity to infinity, what's the area under this whole thing if it represents the bell curve? 1, for sure. Very good. Right. So the area under this whole thing on the whole real line is 1. Okay. That's deeply difficult to show, but it's true. Okay, we'll prove that in Calc 3. Join me. Okay, so very good, nice, good answer, right? So you can prove in Calc 3 that the area under the whole thing is 1, and so the area gives. There is no stats without this function. There is no statistics without the integral or the area under this curve. Okay. And by the way, that's all statisticians do. Statisticians just do try to come up with this curve and then find the area under it. Okay. All right. So that's why it's useful. Okay. That's why. That's what. Okay. 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 So I'll take any questions about anything we've talked about so far.
So are you more likely going to have us just do the right import method, or are you going to have us do all 3?
Oh, it's probably one or the other. Only because look what I just did. I mean, look what I could just go here and get it in an instant. Why am I going to have you like spend all this time doing that arithmetic? Okay. So I'll ask one.
So we're going to need to draw the little box.
Oh, okay.
We're
So
supposed to draw the whole thing, like.
here's what I'm going to
the
ask.
answer.
Yeah, let's just get to the point. Here's what I'm going to ask. Question number 2. Here it is right here. Oh, wait, let's go ahead and put this. So question 2 on the exam. All right, it's going to be something. I want to move this. For f of x equal to, who cares, x to the 7 on the interval of 0 to, let's say, 0 to 4, approximate area under F using whichever method you like.
That makes the 7th area squared.
To the 7th.
Okay.
Any method that you like. And let me say, 4 rectangles.
Using what method?
Any method you want. Right endpoint, left endpoint. I'm sorry.
Did you go there? Yeah, that.
Whichever.
Oh.
I'm sorry. And I'll say n equals 4.
That's also why you can't just watch the videos.
Oh yeah, I know. Yeah, that's right. That's right. Or you can't just read the PDF. Yeah. There's a question? No. Yes.
Oh, are we going to be able to use our calculators anytime during this course?
I don't think so. My mind is open though. I can change my mind. You let me know when you'll need it.
Okay.
Yeah. If you think you'll need it, I will be open to. Yeah. But do you need it so far?
No.
Oh,
Well,
okay.
I mean, X over is, wait, never mind. Let's see what's-
Okay. Let me know when. Let me know when you think you'll need it. Okay. All right. So let us now give the definition. All right. So the definition of the exact area
The integral limit.
right? Exact area under the curve. Right, so let f be a function, and it's not necessary, but in this context, we want f to be continuous on the whole real line. I'm sorry, on the whole interval in question. So let f be a continuous function on the interval a to b. Let's go through this procedure. What did we do first? What did we do? Absolutely right. 1, break a to b. Some people like the word partition. I like partition too, but partition a to b into n equal pieces. All right, so now we're just detailing what we did. Each piece let's go ahead and say this. We'll call the length delta x. Call the length delta x. Now what? So I guess I should say that gives us what? That gives us the width. Okay. Of the rectangles in question. Okay, and now what? We need the height. So in each step interval, in each piece, pick a place x, I, star, where you would like the height to be. That was the next thing that we did. That gives us the height. I'm gonna have to talk about summation notation in a second. Is that okay? Now what? We have the width and the height. What do we do now with those two things? We multiply them, right? So multiply and add. Right? So let's go ahead and make it clear. The height is f of whatever place you pick. That's the height. Delta x is the width. Right? So multiply and add. And so the first one, the height of the first one is delta x. I should say the height of the first one is f of x1. F of x1 times delta x. The height of the second one is f of x2 times the width. And this should be, I can put stars if I want. And then f of x3 times delta x. And then I'm going to add these up all the way until the last one, f of xn times delta x. That is the approximate sum. And then finally, what do? We want the exact answer. How do I get the exact answer? Right. So then we have a term for that. We take the limit, right? So we take the limit as in tends to infinity of this thing. And that's the exact area. And that's also what we're going to call this, the integral from a to b of f of x dx. Okay. So this looks like an S, and it looks like an S because we are summing things up. We're summing things up. Now, I want to talk about summation notation a little bit. I don't want to write this out like that, right? So let me introduce it. But I'm going to take any questions about what I'm asking for number 1 on the exam. There's a definition in the book. You can use that definition too if you prefer. Okay. But when I say define the integral from a to b of f of x dx, then this is what I would like to see. So I need a statement about the width of a rectangle, the height of a rectangle. You need to multiply and add, and you need the limit. Right? So you don't have to be as verbose as this, but these crucial elements are all necessary. Right? If you drop the limit, I'm getting 0. Now, I'm not being mean. Well, you may think I'm being mean. But I'm literally giving you the question. So it's hard to give partial credit when I'm telling you exactly what the question is. Okay? So it's gonna be hard for me to put 0. I probably won't, right? So don't call my bluff, though, right? But please, if you don't write anything else, you need to tell me how you got the width, the height, that you're multiplying and adding those two, and then you're taking the limit, right? Those are the crucial elements for the integral. Okay, I'll take questions on that about what I'm asking for number 1. I hope that you're wondering how anyone ever gets an F in this class. Right. And so most of the time, I give all the questions, I give all the answers, right? There's usually effort. Yes, sir. Absolutely, thank you. And that's the nice thing about Smart Notebook is that it won't let me. I can't go crazy. People always tell me to go back. So I can't fill up every board. I think Erickson does that. He just fills up every board relentlessly. And I just love it. Sir.
So what was the limit of the one we stated before? It wasn't
The limit of what? Of x squared? Of x squared? It's supposed to be 1/3. That's the limit. So for the one we did, thank you for your question. That's good. I think they were asking you about what was the area under x squared? What was that limit? Is that what you were asking?
The first one we did of X squared.
Of x squared. We have not worked that out, but let's work it out. X squared. Let's do this one. Let's do that one. Let's figure out what it is. Now the claim is that it is 1/3. Okay. All right. So x squared. I think I want to take this. Where are you? There we are. Let's see how good it is. So if I say copy and paste here, copy that. Is it going to copy everything, or is it just going to give me the x squared? I think so, right? It does. All right. So now let's work this out. The claim is that this is 1/3. All right. So here's how we prove that. Okay. So now we need to take the interval 0 to 1. Take the interval 0 to 1. We'll break it into n pieces. Oh, I think I can get some extra credit in a second. All right, remind me to get some extra credit. Each interval is of length what? No, n pieces. N pieces. Right, 1 minus 0 divided by n. That's 1 over n. Right. I want the exact answer. Right. So delta x is 1 over n. Okay. What method you want to use? Say it again? Let's use the right one. The middle one's going to create some implications. Right, so let's use the right endpoint method. Okay. And so let's look at some of these points. Let's look at some of them. 0 to 1. This is 0. That's 1. Right, so what is x1? x1 is what? What's the first one? So I'm going to break it into pieces, right? It's supposed to be all the same length, of length 1 over n. If this distance is 1 over n, so what's that number? Here's 0. 1 over n distance. What's this number? Thank you. 1 over n. And if I go another 1 over n, this is 2 over n. Is that okay? This is 3 over n. 4 over n. Right? So, and that's n over n, which is 1. x1 is 1 over n. x2 is 2 over n. x3 is 3 over n because I'm using the right endpoint method. Right? Questions about that? F of x is x squared. So now, what's the area of the first rectangle? That's the area of the first rectangle. Well, the distance is, the width is 1 over n, but what's the height? The height is f of what? x1, so it's f of 1 over n. Right? That's the height times the width. Any questions on that? But what does f do? What was f again? It squares it, right? So it's 1 over n squared times delta x was 1 over n. Is that okay? The second. What about the second one? The second? What would it be? Which one is it? It's 2 over n. That's right. 2 over n squared times 1 over n. All right? And then we can roll all the way down. So what's the kth one? I've been using i's. What's the ith one? Not I. It's I over n, right? So I over n squared times 1 over n. Okay? And then finally, the nth one is 1 over n. I'm sorry, it's 1 squared, not 1 over n. It's 1. It's n over n squared times 1 over n. So it's n over n squared. And that's the last one, times 1 over n. And I need to add them all up. Okay? So it's this plus this plus this plus this. And that's what I'm about to write on the next slide. Questions about this? So that's just what's going on when you don't have, it's the same thing as if we had 5, but now we have an arbitrary amount. Okay? All right. So now it's 1 over n squared times 1 over n plus 2 over n squared times 1 over n plus 3 over n squared times 1 over n plus dot dot dot. Let's say I over n squared times 1 over n. Keep going. Plus finally n over n squared. That's n rectangles times 1 over n. We have to take the limit of this as n goes to infinity. Now, of course, we're saying to ourselves, how in the world did he get 1/3 so quickly going through this whole process? All right, so each one of these, right, has 1 over n in common, right? So it's 1 over n times, and then 1 over n squared plus 2 over n squared plus 3 over n squared plus dot 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 n over n squared. Okay? And then we'll continue to simplify. And the reason why we're simplifying is because we want to take a limit, hopefully. Well, the square is the numerator and denominator of each one. So it's 1 squared over n squared plus 2 squared over n squared plus 3 squared over n squared plus, and that's just n squared over n squared, right? Bear with me. Go ahead.
How come you left out I over n?
Oh, I could have put it there. I decided to just leave it out. Yeah. I'll remark now that each one of these has this n squared in common. I can pull that out. So I'm going to pull that out too. Right? So this is 1 over n squared. Now, if I pull out n squared, this leaves us with 1 over n to the third, right? So 1 over n to the third times 1 plus 1 squared plus 2 squared plus 3 squared all the way up until n squared. And I want to take the limit of that as n goes to infinity, and that is not obvious. Okay. What in the world is the sum of the first n squares? What is that? What is that? I guess I'll add that as a remark. Let's look at it. 1 squared plus 2 squared. Well, let's just do 1 squared first. 1 squared is 1, right? 1 squared plus 2 squared. What is that? 5, okay. 1 squared plus 2 squared plus 3 squared. What is that? 14. 1 squared plus 2 squared plus 3 squared plus 4 squared. What's that? 30. I'm not seeing a pattern. I don't know what that is. So now let's do some research. Let's see if we can find something. What's the sum of the first n squares? Some of the first n squares. Sum of first n squares. Are they going to be nice to us? I actually want to see an image. What is it? What is it? I don't know why his face is there. That's funny. Oh, it seems like that's it. N times n plus 1 times 2n plus 1 over 6. All right, so let's see if that's it. All right, so that's not going to be helpful, I don't think. All right, so the sum of the first n squares, n times n plus 1 times 2n plus 1 over 6. All right, so now I have to go do some research to figure out what that is. Okay? You can prove that by induction, right, which my math majors will be doing a lot in the future, particularly in discrete. So apparently, looking on the outside, this is equal to n times, what was it? N plus 1 times 2n plus 1 over 6. Okay, so we got that from some research. Okay. Questions about that? Let's do a little bit of simplification. I can still extend here. The n's cancel. This is n plus 1 times 2n plus 1 all over 6. And there's an n squared down there. So that is the approximate area, okay, within rectangles. So within rectangles, using the right-hand endpoint method, that's the approximate area. And of course, now to find the exact area, we need to take the limit as n tends to infinity of this. And what's the limit as n tends to infinity? What's the highest power in the numerator here? Highest power when you multiply out? Right, so there's an n squared in the numerator. There's an n squared in the denominator, right? So let's go ahead. I guess we need to work this out. This is the limit as n tends to infinity of n squared plus, let's be good, 2n squared plus, is that 3n? Yeah, plus 1 all over 6n squared. And so now we're taking the limit of these two polynomials. These two powers are the same, and so what do? It's just what over what? 2 over 6. Whew. 2 over 6, 1/3. Right? That's what you do, right? Yeah, good. Okay. Okay. So that's how you get 1/3. That's using the definition. Okay. Questions about that? I guess the real question is, am I going to put that on the test? Right. And so I'm not going to do that. I'm not going to do that. But I hope that you can see the brilliance of this, right? So if I want to know the integral from 0 to 1 of x squared dx, it's 1/3 by definition. But what we're going to do is that we're going to remark that a function whose derivative is x squared is 1/3 x to the third. If I took the derivative of 1/3 x to the third, that is x squared, right? Do we agree with that? The derivative of 1/3 x to the third is x squared, right? And if I put in 1 and 0 and subtract, that is 1/3. Right? And so if I evaluate this from 0 to 1, then I get 1/3 times 1 cubed minus 1/3 times 0 cubed, and that is 1/3. And that is how we're going to get 1/3 instead. That is the fundamental theorem of calculus. Okay, so one line That one line takes care of the whole definition. So we're going to prove the, I don't know if we're going to prove the fundamental theorem of calculus, but we're going to state the fundamental theorem of calculus, and that might be the first question on every exam, because that's the most important theorem in all of mathematics. Okay. Here's the extra credit. The extra credit is due with your exam. So you turn it in with your exam, because I add the points right to your exam grade, okay? Show using the definition that the integral from 0 to 1 of x to the third is what? What is it? 1/4 for sure. So the way that that proof goes is that you just do exactly what you've done here, except for x squared, you have x to the third. What is it that you're going to have to do, though? Begins with an R. Research, right? Because now you're going to have your own formula that you're going to have to find for the sum of what? The sum of cubes, right? There's some formula for the sum of cubes that you're going to have to use here. I'm going to need the source, okay? So tell me what source you got, or if you get way more extra credit if you actually prove that formula. But look it up, and then whatever the sum of cubes is, and then when you take the limit, you should get 1/4. All right. Your name? Nadeem. Even or odd? Even number or an odd number? Even. We'll make this worth 8 points. Test. I'll add it right to it. It's got to be flawless. So come, bring it to me. I'll look over it, see what you need to check. All right. We'll add that to the exam. We'll end with that. Next time we will state the fundamental theorem of calculus and do the shortcut stuff that we love doing, okay? Yes? I think so, yeah. I think that's good. For Calc 1, you don't.
Yeah, I did.
Yeah. The bookstore. The bookstore has codes. Yeah. I think you're supposed to be able to go right into Blackboard. Yeah. Yeah, do not go through the website. Do not go through the website. Do not go through the website. Go through Blackboard. Not if you go through Blackboard.